Hello again, oceanography students. So this is the final lecture video on climate change. So in this video, we're going to talk about the effects of climate change. So here are some of the things that we're going to talk about: melting ice or increasing melting ice, changes in deep water or thermohaline circulation patterns, rising sea levels, increasing acidity of the oceans, and increased extreme weather events. Okay, so in your assignment in the climate change report, you were asked, has the amount of sea ice changed over time in Hudson Bay? And the graph that you looked at showed you this, and unfortunately I've been unable to get data to make this go farther into the current scenario. But what you should have been doing, again, these little dots are from one year to the next, and we're going to obviously see variability from one year to the next. But what you should be paying attention to is the red line. So as you can see, the red line is a negative slope, meaning that the amount of sea ice in Hudson Bay in November is decreasing. So let me back up to what you had been asked about previously, and that is, how does the extent of sea ice change over the course of the year? So this is the northern hemisphere, right? So the northern hemisphere is going to experience summer the same time that we're experiencing summer. So that's going to basically be like June, July, August. That's a normal summer. And then winter is going to be like December, January, February. So what you should have seen is that we had a decrease in sea ice with the least amount occurring over at the end of the summer. And then you started to see sea ice come back at the beginning of the winter. So in previous times and previous decades, Hudson Bay would be covered in sea ice by November. And so the polar bears that live there would be able to walk out onto the sea ice and begin looking for food. So the fact that we're seeing less sea ice in November means that the polar bears are having to wait longer to go back onto the ice. And then you've got a bunch of hungry bears living around people, and that could obviously cause lots of problems. So if you were to, use a piece of paper or whatever to extend this line to see how far it goes, it looks like it goes to zero at about 2015, meaning that there would be, according to this data, we would expect that there wouldn't be any sea ice in Hudson Bay in November. Okay, so again, meaning that polar bears would have to wait until December till the sea ice came back. So let's actually look at some images. Okay, so what we're seeing here is sea ice extent in 2016. And as you can see, this is Hudson Bay right here. You see no white. That means that there is no sea ice there. And that's November 27th of 2016. So if we compare 2015, 2016, we see that there was some sea ice, but it was not covering all of Hudson Bay in 2015. So our projection of that graph was actually correct. If you've got polar bears over here, they're not going to be able to go onto the ice. There's no ice over here. And in 2016, there is no ice at all. So what does this mean for the rest of the Arctic? So here we have Arctic sea ice in September of 2016. So this is tied for the second lowest on record of how far out the sea ice is going. Here we have 2017, which is the 8th lowest on record. Here we have 2018, which is tied for the 6th lowest. And then again, here we have September 2019, and that is tied for the second lowest, again with 2016, which I showed you, and with 2012 and 2007 as well. So all of these lowest extents of sea ice in the Arctic are occurring very recently, in the last decade. Okay, so models predict that climate change will have a dramatic effect on the polar regions. So there's a term called Arctic amplification, which essentially means that the Arctic is warming faster than other regions on our planet. Now, why is that occurring? Well, it's basically what we would call a positive feedback loop. So if the Arctic warms, then we have increasing melting of polar ice. If there is less polar ice, then that means that there is less sunlight that gets reflected, because remember that ice has a very high reflectivity. So if there's ice there, then the sun gets reflected and less heat gets absorbed. But if the ice melts, then the surface is water, which is not as reflective as ice is. So instead, more of the heat is absorbed, which makes the water warmer and the air warmer, which leads to melting of more ice, which makes the water and air warmer. It leads to more melting of more ice, so that's a positive feedback loop, right? The first step is basically all of the changes that occur after that first step are reiterating that first step and intensifying it and increasing it, okay? So no ice means less solar radiation reflection, meaning increased water temperatures. Again, that's called a positive feedback loop. So we could see loss of greater than 2 million square kilometers of ice, or we have seen the loss of 2 million square kilometers of ice in the last decade. We've seen large areas of the Arctic Ocean with no ice at all. And it's predicted that by 2030, there could be 0 sea ice in the summertime in the Arctic. Okay. So how does this affect the animals that rely on the sea ice? I was already mentioning polar bears, but then you've also got a lot of other animals that are relying on that sea ice. So, we think of polar bears, we think, what do polar bears eat? Well, polar bears eat seal pups for the most part, and seal pups need to have ice to be birthed. So if there's no ice, then the moms don't have any place to have their pups and take care of them. And so therefore, the seal population declines. If the seal population declines, the polar bear population declines, and you've got, kind of this chain effect that's going to happen all the way down, basically the food chain. So, a lot of different animals can be affected by this change in sea ice. Now, of course, animals can be affected by the warming of the water as well, even, away from the Arctic Ocean. We're seeing coral reefs dying because the temperature of the water is so high that basically the zooxanthellae are either leaving or being kicked out of the coral or whatever, and that coral is then suffering and dying in return. So I'm going to talk about another way that the coral is affected in just a little bit as well. But basically, all of the animals that are living in the ocean are going to be affected, right? The high specific heat of the ocean makes it so that the temperature doesn't change very quickly in a natural circumstances. But if we do see that we are increasing the temperature of the water at a greater rate than what is normal for animals to be able to adjust to, then the animals can't adjust and they end up dying, or the ones that can end up being able to survive. But that decreases the biodiversity in the area, meaning that decreases the number of species and number of animals that are there, which is not a healthy environment. Okay, what about the effect of warming on thermohaline circulation? So remember that deep water circulation is driven by cold, salty water, right? You've got sinking water here by Greenland, okay? And we've got sinking water here by Antarctica. So that sinking water, why is it sinking? It's sinking because it's high in density, because it's salty, and it's cold. Okay, right? When the water gets cold, then we have ice forming at the surface, and you have the fresh water being pulled away and salt water being left behind, and therefore it's saltier. So not only is it cold, but it's also salty, and therefore it's very dense. So that's going to, sink down and push all of the water around, and cause this huge scale circulation pattern. Now notice that the Antarctica and Greenland here are white, which means that they're covered in ice. So if our global temperature is increasing, then what is going to happen to that ice? Well, it's going to melt, and that ice is going to melt and it's going to flow into the water. What does that do to the density of the water there? We have fresh water entering in, and therefore the salinity is going to decrease. And which is more dense, salty water or less salty water? Salty water is more dense, but if you're decreasing the amount of salt in the water, then that is going to lead to less dense water, which means that although the water may still sink because it's cold, it's not going to be sinking as quickly and pushing the circulation around the ocean as quickly. Okay, so remember that deep water circulation is driven by cold, dense water forming in Antarctica and the North Atlantic. So what if the climate warms and the glaciers start melting? We have fresh water that runs off and makes the water less dense and stops or slows the formation of bottom water. It's been proposed that if the water stops flowing so well, then that could lead to extreme cooling in Europe, because Europe is relying on the Gulf Stream making its way all the way to the other side of the North Atlantic Ocean, and that's a warm water current. So if that warm water current isn't moving over there as quickly, then that could lead to cooling. However, I have seen some reports that the thermohaline circulation, or actually surface currents, I think is what they were measuring, have actually increased. So we don't, it could be that deep water circulation is going to slow, or it could be that surface circulation is going to speed up so much that that could actually mean that surface currents are faster, but deep water circulation is actually slowed. So we don't really know at this point what could happen, but these are all of the possible scenarios. Okay, what about sea level? Okay, so here we have sea level in November. And so again, you should be paying attention to the red line. So you should have said, oh yes, sea level is increasing in November. And the average rate of increase globally is about 3 millimeters per year. So if Antarctica melted, then the global sea level would rise 60 meters. And that's 200 feet. If Greenland also melted completely, then the sea level would rise another 7 meters. That's another 20 feet. So that's 220 feet of sea level rise. Now, places that are lower lying are going to be more affected than places that have a sharper coastline, if you will, right? So if you go into estuaries, then the estuaries are definitely going to be inundated with water. Whereas if you go along the coast and you've got, maybe a erosional coast where it's already very narrow, you're not going to see that sea level rise. You're not going to see the sea coming in, the water level rising and intruding on the land as much, because you've got these big cliffs that are blocking it. But what's going to happen to those cliffs? Well, probably more erosion is going to happen there. So if people have their homes on the cliffs or close by, over time, that cliff is going to erode from the increased wave activity higher up along the cliff line. Okay, so here is a map that's showing you climate anomalies and events in 2014, and you can see that there are climate anomalies everywhere. Now, why does this matter? And here's another one from 2015. Basically, they put these out every year, and every year it's the same thing. We're seeing, new events in places that haven't been experiencing those events. Now, why is this such a big deal? It's a big deal because the governments there aren't used to having to deal with these problems, right? Flooding occurs when you have an area where it's been dry, and therefore the a heavy downpour is going to mean that the ground isn't able to absorb the water as well. So instead, the ground acts more like concrete than it does dirt, and you have flooding that occurs. Places that aren't used to low amounts of rain, you end up with droughts. Places that aren't used to hurricanes don't have the infrastructure in place to be able to handle all of the people that need to be moved and housed in new places. So there are all kinds of things, and it's not just in certain areas, it's all over the world. Okay, so what climate change results in are extreme weather events. So an increase in water temperature could mean an increase in intensity of hurricanes, which is basically what has been predicted for a long time and what we are actually seeing pan out. So what that means is that we're seeing in a given hurricane season, we're seeing that there are an increase in category 4 and 5 hurricanes, which are category 5 is the highest you can get in the hurricane for hurricanes. So we see basically increased intensity, frequency, and duration. So we have, they're higher wind speeds, they're happening more often, and they're lasting longer. They're not, you normally see these hurricanes that kind of, they hit land and they fall apart. Well, in a lot of examples, we're not seeing them fall apart as easily, and we're not seeing them move. We're seeing them stay in one place for a long time. For example, there was a hurricane in Texas a couple of years ago that it made landfall and it didn't lose its intensity. Why didn't it lose its intensity? Because it dropped so much rain on Texas that the water on the land actually continued to power the storm. Normally, if the storm goes over land, there's no more water to continue to power it, right? It's the warm water that is powering that low pressure system, which is a hurricane. So if you get over land, then usually, it's not powered anymore, and so it falls apart. But in lots of instances, if there's so much rain that falls down on land, then there's water that is then supplying more energy for the hurricane. So there have been 5 category 5 hurricanes in the Atlantic in the last 4 years, which is a record. So last September 1st, 2019, Hurricane Dorian hit the Bahamas, and it was the second strongest Atlantic hurricane on record. We had that same year, we had quite a bit of damage that was seen from Atlantic hurricanes. So Hurricane Barry hit Louisiana, causing $600 million in damage. Hurricane Dorian, again, hit the Bahamas. It also hit Southeast U.S., and that costed $4.6 billion in damage. Tropical Storm Imelda hit Texas and Louisiana, causing $2 billion in damage, and Tropical Storm Ferdinand hit Northeast Mexico and caused $250 million in damage. So all 4 of those storms moved really slowly. They moved at 8 miles per hour or slower, meaning that they were staying in one place for a long time. The average speed of movement for a tropical cyclone is 11 miles per hour. So these were moving at a slower rate and staying over land for longer and causing a lot more damage because of it. Okay, so we see increased intensity hurricanes caused by climate change, which, is very predictable, because if you have increased water temperature, that's going to increase the intensity of low pressure. Okay, we also have seen activity of tornadoes increase. We've seen increased heavy downpours. So that means basically rain falling, a lot of rain falling in a short amount of time, which of course leads to flooding. And we've also seen extreme droughts and fires in our area and other places in the Southwest as well. In Texas in 2011, and also I think that this was also hitting Oklahoma. There was over 100 days where the temperature was over 100 degrees Fahrenheit, and I cannot even fathom that with living in our fairly mild climate. Okay, so this is showing you the temperature change over the United States. And this is basically, you know, we take a comparison of a certain period of time and what was the average temperature then, and then we compare it to what the temperature is now. So you can see that pretty much almost everywhere in the United States has experienced an increase in the temperature. And this map is showing you an increase in very heavy downpours, very heavy precipitation. So again, the majority of the United States is experiencing increased heavy downpours, whereas Hawaii is actually increasing, has decreased heavy downpours. Okay, another thing, let's jump back into our ocean friends and see how they're being affected by this. Another thing that is occurring in the ocean is something called ocean acidification, which you know, essentially in summary means that the ocean is getting more acidic over time. Why is the ocean getting more acidic? Well, it's because the carbon dioxide in the atmosphere ends up going into the ocean. So we not only have increased carbon dioxide in the atmosphere, we have increased carbon dioxide in the ocean. Now, once the carbon dioxide gets into the ocean, it basically bonds with water and it turns into carbonic acid. That carbonic acid basically then lowers the pH of the seawater. It frees hydrogen ions, which lowers the pH, and it dissolves and then can bond to carbonate to form bicarbonate. Now, why is that important? That's important because the majority of animals that have shells make those shells out of calcium carbonate. If there is less carbonate in the water, then that means that there is less, the shell building organisms have less ability to make their shells. So I've posted a video on this, so you should go and watch that video as well, and explains kind of what's going on with ocean acidification. But here I have some pictures that show you a couple of experiments. So this is the shell of a pteropod. So this is where the pteropod was put in water that had the acidity that was predicted for the year 2100. And you can see that over time, that shell deteriorates. So not only is it that as an organism is building its shell, that it can't get enough carbonate to get its shell bigger, with the acidity of the water, that also means that the shell material will end up being dissolved and broken down. Basically, you know, it's the same thing as if you were to take a tooth and, you know, put it into carbonated water over and over for a long time. You would see that that tooth would start to shrink because it's dissolving in that water. Okay, the bottom picture here is showing you clams that were put in a pH of 7.5. This is basically starting at the beginning what the shell looked like. B is showing you what it looked like after 24 hours in that, and C is showing you what it looked like after 72 hours. Now, remember that a pH of 7.5 is actually still basic. So we're not talking like, you know, we're not talking about lemon juice. We're talking just like slightly more acidic than what the ocean is already. Okay, and then this over on the right side is showing you scallops. So this is scallops at 250 parts per million CO2. This is at 390, this is at 750, and this is at 1500. So as you can see, the scallops in the increased acidity water grow much smaller than those ones at the decreased, the more alkaline water. So why should we care? Well, I mean, I showed you a couple of things about extreme weather, right? Extreme weather, it kills people, it destroys people's homes, it ruins crops, it can lead to famine. And, you know, other than just looking at us, we should also be thinking about the health of the planet as a whole, because we do rely on the health of the planet. We rely, lots of communities do rely on fish and other resources from the sea. So You know, organisms in the ocean are very sensitive to sudden temperature changes, and that could lead to, you know, major declines in populations and possibly even extinctions. You know, ocean acidification not only affects the big-shelled organisms that we're talking about, it also affects those little tiny plankton that use calcium carbonate to make their shells, such as coccolithophores. Okay. Now, the overall, you know, if you were talking money here, the overall cost of, you know, not doing anything could be anywhere from 2 to 20% of the gross domestic product. So, you know, not only is it, you know, harming people's lives and then their homes, you know, decreasing amount of food, causing a decline in the organisms in, you know, not only the ocean, but of course on land. I didn't really talk about land at all, but of course, you know, terrestrial animals are affected by this too. But it's also, you know, monetarily expensive. So this graph here is showing you scenarios of what the temperature change could be depending on, you know, if we change. So the black line starting out here is the average temperature. And then that black line splits into 3 lines, a red line, a green line, and a blue line. The red line is showing you what happens if we, I think it's if we continue with the growth that that's happening right now. So basically the red line is what's going to happen if we continue our normal use of fossil fuels and we continue to have a steady increase in carbon emissions, basically going from 9 billion tons per year that is put out into the atmosphere to about 28 billion tons per year in the year 2100. Okay, then you've got this this green line here, which is assuming that humans will kind of balance out the use of fossil fuels with other non-carbon emitting sources of energy. So we're basically, this means that we're using you know, increased renewable resources. And then the blue line is basically saying that humans worldwide will make, you know, more sustainable choices, and they're going to be, you know, more renewable energy sources. And under that scenario, that would mean that carbon emissions would projected to increase from today's rate of 9 billion metric tons per year to about 12 billion tons per year by the year 2040, and then gradually decline back to 1990 levels, which is 5 billion tons per year by the year 2100. So, you know, essentially red, continue on in the path that we're going, green, make some changes, blue, make a lot more changes, basically. Okay, and so what does blue tell us? It tells us that the increase in temperature is going to be 2 degrees Celsius, the green is going to be 3 degrees Celsius, and the red is 4 or more degrees Celsius, and that is the increase. Okay, and remember that this is in degrees Celsius, it's not in degrees Fahrenheit. So that increase is much more than what you would see in degrees Fahrenheit. And actually, Fahrenheit is on the left side over here. So for comparisons purposes, if you know, the blue is 3.5, an increase, an average temperature of 3.5 degrees Fahrenheit, the green ends up being about 5.5, and the red is looking like it's about 7.5 degrees Fahrenheit. So that would be the global average temperature, right? Of course, that doesn't mean that every place on the planet is going to see an increase of 7.5 degrees Fahrenheit. Some places might experience a greater increase, and some places may experience a lower increase, increased rate. Okay, so here is another kind of projected change in average annual temperature. So this is if we make major changes, right? We are, you know, we do see an increase in temperature. If we continue with the way that we're going, this is what our planet will look like as far as increasing temperatures. Okay, so what can we do? So the cost of action is only 1% of GDP. Remember that inaction is somewhere between 2 and 20%. So it seems, fairly obvious to me that you spend a little bit of money to keep yourself from losing a lot, right? So what can we do, individually? Well, reduce plastic consumption. And why do I say reduce plastic consumption? I say reduce plastic consumption not only because plastic is, often ends up in the ocean and, it's basically a problem because plastic never goes away. Basically, every plastic that has been created in our lifetime is still on our planet, which is, a crazy thing to think about. But that's not the reason that I'm saying this. The reason I'm saying that is because plastic comes from fossil fuels. So the creation of plastic actually puts carbon dioxide into our atmosphere, okay? Another thing, drive a fuel efficient vehicle and maintain it so that it stays fuel efficient. If you can ride your bike or walk instead of driving, then do that whenever you can. It's also good for your health too. Of course, if there are pieces of legislation that curb the production of fossil fuels, you can support those. You can write to your legislator. Support legislators then that fight for renewable energy. Look at what their platform is on climate change and on renewable energy and on higher standards for vehicles before you decide to vote for them. Buy recycled goods and also recycle yourself. But of course, this is not the best thing because lots of times our goods are not actually recycled. So don't buy a bunch of plastic stuff thinking, I can just recycle this, because it's not necessarily the truth. Okay. Support companies with green practices, and you could even call companies and say, what are you doing to fight climate change, and tell them, well, I'm not going to buy your goods anymore. Obviously that takes a lot more effort. Buy products locally, because that means that they haven't had to be shipped to where you are. And you're also supporting your community. So that's two good things. Keep your house properly insulated and check your thermostat, and basically don't crank up the heat all the time, and don't crank up the air conditioner all the time. Let your body adjust to temperature changes, seasonal changes in temperature. You don't have to, keep it freezing in your house or keep it really hot in your house. Okay. And then another one that I've added in here is eat less meat, because I've had students that are like, hey, how come you haven't added that in? Meat production is important because cows do produce methane, and I think it's often said that it's farts, but I think it's actually burps that are producing the methane, because they've got bacteria in one of their stomachs that help to digest the grass, and those bacteria are what are releasing the methane. So if you eat less meat, what that means is that the rancher is probably, not going to be selling as much cattle to be, slaughtered and turned into meat, which means that they're going to inseminate less females and produce less calves, which means that overall on their ranch, they're going to have less cows. And that is going to mean a decrease in methane production. Okay. So here you have an extra credit opportunity. This is going to be applied to the final exam. So for this extra credit assignment, you are going to write a letter to a friend or a family member. Okay, so the wording in this letter should be appropriate for talking to your friend or your family member. And what you're going to do is you're going to explain climate change to them. And you need to assume that they haven't taken this class and they don't know all of the things that you've learned in this class, so you have to teach them. So included in your climate change letter, you should include what is climate change, what causes it, including what fossil fuels are and how they affect our atmosphere. Explain the greenhouse effect, including what are the important greenhouse gases and what happens if the greenhouse gases increase and what happens if greenhouse gases decrease. And then what are the effects of climate change? So how could the atmospheric or oceanic circulation be affected? And I don't think I talked about atmospheric a whole lot, but you could think about what would happen if, globally our temperature is increasing. What would happen to our atmospheric circulation pattern? Remember, we've got rising air and falling air and wind patterns that are created. I did hint to one thing is that we have seen some increased wind production, especially up towards the northeast. And then also include an explanation of what's happening as far as ocean acidification goes. And then finally, what are some marine organisms that are being affected by climate change and ocean acidification, and explain how they're being affected. Okay, so again, that's an extra credit opportunity. You don't have to do it, but if you do, it will be applied to your final lecture exam. Okay, I hope you have a good night or day.